Hello everyone, my name is Ambika Ashapuri and in this presentation we are going to solve the questions which came in our first internal test. These questions are regarding formal languages and grammar, Backus Naur form, postfix notation, pushdown automata, finite automata, and finally the Turing machine. Okay, so let's get started. In the first question, we have been given a set of some terminals and non-terminals along with some production rules. We have to use the set of productions to show that each of these sentences is a valid sentence or not. So let's try to solve this question. We know that the grammar mentioned above is context-free grammar, and context-free grammar is used to describe context-free languages. Context-free grammar can be described using four tuples V, T, P, S, where G is for grammar and T describes the finite set of terminal symbols. V describes the finite set of non-terminal symbols. P describes a set of production rules and S is the start symbol. Our first sentence is the happy hare runs, and from the production rule we came to know that the start symbol is the sentence itself. And the sentence is the noun, phrase, transitive verb, phrase, noun, phrase. And if we will write their equivalent terminal symbols, we will get to know that the sentence happy hare runs is a valid sentence. And in a similar manner, the sleepy tortoise runs quickly is also a valid sentence. The tortoise passes the hare is a valid sentence. And finally, the sleepy hare passes the happy tortoise is also a valid sentence. In question number 2, we have to construct derivation trees for the sentences mentioned in the previous question. Okay, a derivation tree or a parse tree is an ordered rooted tree that graphically represents the semantic information of strings derived from a context-free grammar. It has three major components, which is root vertex, which must be labeled by the star symbol, vertex labeled by non-terminal symbols, leaves, which are labeled by terminal symbols or epsilon. So the first sentence, the happy hare runs, and as we know that the start symbol is the sentence which can be branched into two phrases which are noun phrase and intransitive verb phrase. Noun phrase can be further be classified into article, adjective, noun, and intransitive verb phrase into intransitive verb. And then finally we can write their appropriate terminals, which is the happy hare runs. And in this way we have made the derivation tree for the sentence the happy hare runs. In the similar way we can make or construct the derivation tree for the sleepy tortoise runs quickly, and this is how we can do that. Okay, and for the sentence the tortoise passes the hare, this is the derivation tree, and the sleepy hare passes the happy tortoise, this is the derivation tree for that sentence. In question number 3, okay, we are now on question number 3. In question number 3, we are asked to construct a phrase structure grammar that generates all signed decimal numbers consisting of a sign, either positive or negative, a non-negative integer, and a decimal fraction that is either the empty string or a decimal point followed by a positive integer, where initial zeros in an integer are allowed. For this, first we have to understand what a phrase structure grammar is. A phrase structure grammar is a formal grammar that describes the structure of a language by defining a set of rules that specify how phrases can be formed from smaller constituents. In context of signed decimal numbers, we can construct a phrase structure grammar to define the syntax of these numbers. We require production rules for the phrase structure grammars, and the production rules are on the screen. These are the production rules. And this is the code segment which we can implement to form the phrase structure grammar. The second part of the question demanded the Backus-Naur form. The Backus-Naur form of the given grammar describes the syntax using a set of production rules, and the EBNF representation or Backus-Naur form is as follows. Question number 4. Give production rules and Backus Naur form that generates all identifiers in the C programming language. In C, an identifier starts with a letter or an underscore that is followed by one or more lowercase letters, uppercase letters, underscores, and digits. So this is the required Backus Naur form for all the identifiers in C programming language. Question number 5. Give production rules an extended Backus norm form that generates all decimal numerals consisting of an optional sign, a non-negative integer, and a decimal fraction that is either the empty string or a decimal point followed by an optional positive integer optionally preceded by some numbers of zeros. Okay, so this is the extended Backus norm form. In question 6, we are asked to determine for each string whether it is generated by the grammar given for postfix notation. If it is, find the steps used to generate the string. To determine whether each string is generated by postfix notation grammar and find the step used to generate the string, we need to understand the rules of postfix notation grammar, and which are set of some terminals, non-terminals, and production. We can check each string in the following manner. Question number 7. In this, we have been asked to construct a finite automata, push-down automata, and Turing machine to accept the set of L of all strings over 0 and 1 ending with 0, 1, 0. So, this is a finite automata, and here the set Q represents the set of states which are Q0, Q1, Q2, Q3, Q4. Sigma is input symbols 1 and 0. Q0 is the initial state which is Q0, and capital F is final state which is Q3. And this is the required finite automata. This is the required push down automata. And finally, this is the required Turing machine. And this is the state transition table for that Turing machine. In this question number 8, we have been asked to construct a Turing machine that accepts the language, the given language. And this is the solution. Last question. In this, we have been asked to construct a push-down automata equivalent to the following context-free grammar. This is the context-free grammar. We also have to test whether this string is in an affair or not. Okay, so these are the states. Q0 is our initial state, Q1 is the state for handling 0 productions, Q2 is the state for handling 1 productions, Q3 is state for handling 0 in the string. Okay, and Q4 is the accepting state. These are the alphabets. Input alphabets are 0 and 1, and stack alphabets. Here Z is the initial stack symbol. These are the transitions rule for the push down automata. And the push-down automata accepts if it enters the accepting state Q4 and the input state is completely processed. Now, to test whether the given string is accepted by the push-down automata or not, we have to apply transition rules based on the input string, and we will apply them in this way. Okay, and then we came to the conclusion that the string is accepted by the push-down automata. Thank you so much. Here ends our presentation. If you have any more doubts, you can contact me or email me at the following number and or email address. Thank you so much.